Hello everyone. In this section we are interested in finding the length of the curve, also known as the arc length, and subsequent to that we would like to be able to find the area of surface of revolution of that curve, either around the x or the y-axis. It is possible, the methods that we choose, it is possible to find the area of surface of revolution about a line other than the x or the y-axis, and you will see a formula for that near the end of the video. So let's begin with the premise here. Suppose we have a curve. So remember, the functions for us, we call them curves. So there you go. Suppose that is the curve that we are looking at, and we are interested in finding the length of that curve. Now notice, by the way, the curve is not a straight line. If it's a straight line, it's easily found. But if something kind of bends and twirls and curves, then we need to have a different way of doing this. So what we would like to do is, in order to find the length of the curve or the arc length, we're going to partition. First of all, we're going to partition the numbered line from A to B, where A is less than or equal to B, and we would like to create what we call a regular partition. A regular partition, that means a subdivision of the numbered line into equally spaced intervals. So by that we mean the following. See, the distance from x0 to x1 will be the same as x1 to x2, which, if you recall, we typically call these delta x's, delta x, and so on. So these are all equal. Actually, that one was in error, this one, because I have dot 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 here. And there you go. So that's the kth, if you will, if it's the kth arc, and the width of what we're looking at, the partition, is going to be a width delta x. So that's what we're going to do. Now, in order to approximate each of these arcs, so from point 0 to point 1, let's say this is the arc, that's the actual arc, that's the length we are interested in, we can approximate it with this straight line segment. Same thing with the next arc. That next arc could be approximated using the second straight line segment, and so on and so forth, until we get to the kth arc, and there you go. So that's the actual length. It can be approximated by that straight line segment. And then, just like before, what we do is eventually we allow these delta x to be smaller and smaller, so that the error in the approximation of the actual curve using the straight line segments will diminish. And here, so based on that, we have our definition of arc length of a curve. If we have a continuous function on a closed interval from A to B, and we have a regular partition, remember that means the length of each subinterval is of length delta x. Then the arc length of the graph of a function f from point A to point B is given by the limit of the Riemann sum of those individual straight line segments. Remember, that's what the straight line segments are. So d here, that's what this author uses, d p sub k minus 1 to p sub k. That means the length, the distance from that point, p sub k minus 1 point, to p sub k. That would be the straight line distance between them, direct distance, provided the limit exists. So the derivation of actual definite integral for this, because this is the limit of Riemann sum, remember, we can actually define definite integrals using the limit of Riemann sum. So it's worth going over this one. So here's the derivation of the Riemann sum in this case. So we're looking at the distance between right up here. We're going to look at the distance from p sub k minus 1 to p sub k using distance formula. we get the first step. Remember, it's y2 minus y1 squared plus x2 minus x1 squared, the distance formula. And then following that, we simply replace y with f, the function notation for y in both of these. Now, another way, by the way, we could have started this was we can indicate the distance between those two as delta y sub k plus delta x sub k, each of those squared, right? The change in y squared, change in x squared. And in fact, the quantity x sub k minus x sub k minus 1, that is our delta x, right? So this would be the delta x. And what's next to that in the function notation, that is our delta y. Okay, so that's also an alternative to how we could have started this. Now, the next step is when we apply the mean value theorem. And right in here on the left side, I have recalled what the mean value theorem was. If you remember, the mean value theorem tells us if we have a continuous function on a closed interval from a to b, and if we actually draw a secant line, which I have in this case, this is my secant line, from some point P to point Q, let's say here, from P to Q. It is possible, because of the continuity of the function, it is possible to find another line that has exactly the same slope that is tangent to the curve. And the red line is the line in question here. Okay, so and then once we do, for some evaluation point that's going to happen at some point c sub k, right, which we call the evaluation point, inside the closed interval from a to b. Because they have the same slope, well, this is the slope of this line, right, the slope of the line. And the slope of the tangent is going to be the same, right? So m is equal to f prime at c sub k. And the next step is to solve for delta y. So we can write delta y as f prime times delta x, right? And that is indeed what's going to happen here. So this is in fact your f prime at c sub k times delta x sub k, and what's to the left is indeed delta y sub k. Okay, which is again precisely that expression. So hopefully that's cleared for you. Now remember, c sub k is inside of that interval, sub-interval, the kth sub-interval, right? That's where c sub k is in this case. And then you go through a couple of steps of algebraic manipulation. They're simple manipulations. So once we actually replace, notice we replace delta y with f prime delta x. And then of course you square that. And our next step is to actually, because there is a common factor, we can factor delta x here, and we can factor delta x here in their squared form, delta x squared in other words. And then we take the square root. Here we're using the square root, the multiplication rule of radicals. Root a times b is root a times root b. So we can actually take the square root of that portion separately. And once we do take the square root, it becomes just delta x. Okay, so that's that part. And the other part of it, 1 plus f prime at c sub k squared, remains inside the radical. And that is going to be the form of, again, that's just evaluation of the distance, the direct distance between point p sub k minus 1 and p sub k. And then by definition of arc length of a curve that we have up here, we're simply going to replace this quantity d p sub k minus 1 p sub k with the equivalent form. And that's how, from that step to the last step, that's what happened. And indeed, if you look at the limit of Riemann sum, this one, the Riemann sum, we recognize that again as the definite integral, right? The definite integral. And that's going to, from here, that's going to bring us to that definition of the arc length. So they call it the arc length formula. So in this case, we have let a function f be smooth. Now, the word smooth here is actually, this is a technical term for us, remember? A function is a smooth. That means there is no cusp, and there is no jump, there is no corner. In that case, the function would be smooth. Okay. And if that is the case, then the arc length of the graph from point A to point B is given by the definite integral, which is the limit of the Riemann sum. And this is also written in two different forms using the differential form. That's the second part. Remember, f prime of x is indeed dy dx, right, using Leibniz notation. And we can use both forms of that. So this will give you again the length of the curve. Pretty simple idea, simple concepts. Now, and we will see actually an easy way of writing this formula, but that's the formula we want to know. We'll see a really concise way of writing this in a moment. Now, if you are interested in length of the curve with respect to variable y, that's when you interchange the x and the y. And in that case, the formula adjusts in such a way where what used to be f prime x, notice here, we had f prime x, now it's going to be g prime y. The limits of integration, of course, are based on the y-axis from c to d, okay, from lower to higher point. And using Leibniz notation, also you gotta pay attention to this subtle change here versus here. In this case, g prime of y is actually dx dy. In other words, we find the derivative with respect to y, where up here we find the derivative with respect to x. Okay, and there we have our formulas. Now, this will give you the arc length for a fixed distance from A to B. Okay, so it's going to go, let's say in my figure 6 here. So it's going to go from C to D. So I'm looking at that fixed length. Okay, well-defined interval. Now sometimes we actually want to look at the arc length function of a curve. So the difference here is that we have a starting point. Clearly we have A as our starting point here, but if you look at the upper limit, it doesn't go to B. It's not a fixed distance, right? Or it's not a fixed length, I should say, because with distance you would think direct distance between 2 points, whereas here we allow for curvature. So what's different now is that, for instance, if I want to know what is the length of the curve from here to here, I don't want to go all the way to B. I just want to stop here. I want to know how far is that? How long is that curve? Or I can go from there to here and stop here. How long is the curve now? Or I can go a little further, there you go, and cut it off here. How long is that curve? So in order to be able to determine the length of the curve at any point beyond A, where x is just an arbitrary number here between A and B, then we need to have the arc length function. The arc length function looks very much just like the arc length right in here, this formula we have. Remember, from A to B, f prime x squared dx. Now, because it's going up to x, we need to change here the variable t. We need to change it to x to variable t, because these variables cannot be the same. Okay, the variable of the integral, the limit of integration, and the variable in the integrand must be different. So because this is x, then we use alternatively a t for that. But that is the arc length formula. So s of x here is actually the length of the curve. Okay, so the arc length function s, that's what that is. Arc length function s is given by that definite integral. And usually when you work this you're not gonna get a number. You're just gonna get an equation, if you will, and then you put your own x in there. Like for example, if my interval goes from 2 to 10, I can choose x to be 5, and then see what this formula looks like. The formula will give me the length of the curve from 2 to 5. If I change my x to 8, the formula that results from this will give me the arc length from 2 to 8, and so on. Okay. Now, towards writing this arc length formula in a simpler form, we can introduce here, if I look at s prime x, right, s prime of x is the derivative of s with respect to x. So from this, if I multiply, cross multiply, I get ds is s prime x dx. And that is exactly what this expression is. So that quantity is called the differential of arc length. Differential of arc length, that's what that is. Now, we can use the differential of arc length because, again, s prime in this case, s prime is going to be, let me write what s prime is. S prime of x is going to be simply square root of 1 plus dy dx, which is f prime x squared. And then that's what s prime x is, right there. Okay. And so there you have it. Now, using that, we can write our arc length formula. Look at how simple that is. This is what I'm looking at there. Instead of writing square root of 1 plus f prime x quantity squared dx, instead of doing all of that, we just write it as ds. So the entire integrand and the differential of x dx is written as ds. That's all it is. And there you have it. That replaces the radicand in the differential of arc length formula. Okay, and actually this is what I mean in the arc length formula, not differential of arc length formula. All right, and again, this would be easy to remember. Okay, so the length of the curve at any point is simply the integral of the differential of arc length from a to whatever. And here, this is going to, again, clarify the relationship between dx, dy, ds. Remember, ds is based on the tangent line here. Okay, this is ds. And that would be an approximation to the length of the curve. Okay, so that's what that is. To the differential of, if you will, ds is based on the tangent. Let me clarify that portion for you. The change in the curve, the change in the value of the curve from here to here, okay, that is actually delta s. That's the actual change in the curve, in the length of that curve as you go from lower to higher point. That's how much it measures. We approximate delta s using ds. Okay, we're using the tangent. So that same length is approximated to be this much. And clearly they're not the same, but as dx goes to 0 or delta x goes to 0, those two become very close. So that's what that is. Okay. Now, and then we have this other formula, right, which is right up here. Remember, this is the arc length. The one I circled is the arc length function. That means it goes up to any arbitrary point x, but for a fixed interval from a to b now. So x is going to be b now, right? Then we get the familiar formula that we had before. That's going to be the integral from a to b of ds, which we can be written using, again, the differential notation or f prime notation. All right, and we are done with that idea. Next, we're going to look at the notion of surface of revolution. Now, for surface of revolution here, we've done volume of solid of revolution before. Now we actually look at surface of revolution. That means the surface that's on the outside, not the space, the volume that's inside. Okay, so suppose again we have a curve like this and we are rotating it or revolving it about the x-axis. The result of rotation gives you this solid that you're looking at, and we are interested in the surface area, again the area that's on the outside. So using the same ideas for solid of revolution, what we could do is we could actually partition the curve into sub-intervals, right? We can partition the number line, the interval from a to b, into a regular partition, each of with delta x, right? We can do that. And then if you actually look at the actual curve when it's revolved, this is what you get for the first part. Okay, the first part, S1. For from S1 to from point 1, P1 to P2, the spending part, that portion is right here. And then the next piece of that curve is right here. So as these pieces revolve, then they generate the solid that you're looking at here. Okay. Again, we are interested in what's on the outside this time, not on the inside, the volume. So this is actually, at this point, we still, if you can find what each of these surfaces are, how to calculate them, we get the exact surface area. So how are we going to approximate these now? So this is what the process is. Suppose I have an arc. There you go. So I'm just going to do a blow up of that portion. So suppose this is my arc. I'm going to make it bend like that. And if I can actually use a straight line segment to connect it, when you revolve the actual arc, this is the actual arc right here. So you're going to get this solid that you're observing. This is what it's going to look like as a result of a rotation. Now, if I use the red line segment, and that's what this is, then I'm going to get, notice how those two are similar. They look very similar. The difference is one is based on the straight line and the other one is the actual curve that bends. Now, we know those two surface areas will be approximately equal, and if we make delta x small, as you let delta x to go to 0, that means you're shrinking this solid ever smaller, the width of it. So the two solids are going to become even more of the same. Now, if I look at here in terms of the function, so the distance from, let's say, the x-axis in this case out to the outside point, That's going to be f at x sub k, and the distance to the lower point, p sub k minus 1, is f of x sub k minus 1, right? Now the question is, what is this solid, right? Which is trying to approximate the actual solid. Now this turns out to be the frustum of a cone. Okay, and what do we mean by frustum of a cone? The frustum of a cone is this. Suppose I have a cone like so. Okay, so there is a cone. Now if a plane crosses this, if the plane crosses this cone at an angle that is parallel to the base of the cone, and this would be like the impression that it leaves, right? Now imagine shearing off this top portion, right? The plane actually cuts it off. It's like a knife cutting the cone. And there you go. This is what they call the frustum of a cone. Now, and of course here my frustum, this is what the thickness of it is going to be, right? That's going to be delta x, the thickness here, which I've made it very, very big. When you make delta x small, the frustum of a cone is actually going to look something like this. You see how that looks like? Now it's beginning to look more like that. And this is delta x again. So we have outside radius, inside radius again. This is our outside, this is our inside. Okay. So that is what the frustum of a cone is. And that's what these cross sections are going to look like, right? These typical solids, I should say, are going to look like. Now, and then here you can see the derivation of a differential of the surface, delta s, differential of the surface, is going to be what this is. This is delta s. Okay, and that is given by the formula that you're looking at. Okay, so the formula is 2 pi to find the surface area of frustum of a cone is 2 pi times, this will give you, this quantity gives you the average radius, and that's the thickness. Okay, so the formula again for frustum of a cone is 2 pi average radius times thickness. All right, and then because we've already determined what that quantity is, the thickness is, we're going to, let me make, yeah, that's fine. So replacing the distance, the direct distance from p sub k minus 1 to p sub k with what we showed earlier, will result in the next part of the formula, which is this part. And then ultimately we can write this as a limit of Riemann sum, right? That, of course, that's not the limit. I don't see a limit in front, right? That's just the Riemann sum up to n. Without the limit, the surface is only approximately equal to the sum of those individual surfaces based on a straight line segments. Okay, and once you take the limit of the Riemann sum, then of course you get the actual surface area of revolution, which is now 2 pi, again, fx, and then here the fx, this is the average radius again. That's what the average radius is. Okay, and there you have the formula. And remember, this portion of it is the differential of arc length, right? ds. That's differential of arc length. So you can get a more concise way of this formula. And y here is going to be the distance. It's going to be this in my drawing. There you go. That's what y is. Let me use a different color that shows better. There you go. This is what y turns out to be right here. That's what y is. Okay, it's the average distance to that arc, if you will, to the kth arc. And so this is another formula for us. And of course, here again, you're looking at using differential of arc length to approximate the actual. See this bending part, that's the actual. That is delta S. That's the actual arc length. And it's approximated using the tangent line. ds is an approximation. So delta S is approximately equal to ds. If you will, that's what we call an increment. So delta S is an increment of arc length. Okay, and that would equal to the differential of arc length. Maybe I'll write that so you just have it for reference. Delta S is what we call an increment of arc length, whereas ds is the differential of arc length. Okay, and in the last part of this, and then we'll look at some exercises here. What if I'm going to revolve the curve? This would be the curve. What if I revolve the curve about a line, not an axis? So you clearly get this solid, right? Like that. And again, the surface area on the outside is given by this formula. Now this is an exercise in the book, but I'm just going to take it, instead of show that, we're just going to say that this is indeed to be like a definition for us. So let f be a smooth non-negative function on a to b. The area of surface obtained by revolving the graph of f about a line is given by this formula. So it is possible to revolve again about another line. And the same thing holds if you revolve about, let's say, a vertical line. Okay, so you have something in the form of g or y, and you're revolving about a line here, right? So in this case, you're gonna get a solid that looks something like this. So the same methodology holds for other types of regions. Okay, and let's see. Oh, we're almost near the exercises. So if you revolve with respect to y, okay, so the formula we saw up here, that was rotation with respect to x axis. See, that's revolving about the x-axis. So about the x-axis, and this is gonna be like the y here. So it's gonna be 2 pi, and then you multiply times y, and then differential of arc length. Y is the distance to the axis of rotation. So because the horizontal axis is what we're rotating about, therefore it makes that distance be y. If you revolve about the y, then this would be the distance to a typical surface, differential of surface, and that's going to be x. And that's what this is. gy in this case is x. Okay. And you can actually write this in a concise form also. 2 pi x ds. So rotation about the x-axis is 2 pi y ds, about the x-axis is y ds, and about the y-axis is going to be x ds. Some students like to tell me that this is helping them. If you revolve about the y-axis, the integrand will have x in it. But I always draw it and I let the sketch speak for itself. All right, and So that's what that is. Now this, for this particular example, the curve is x equals y cubed. Remember, that's what that looks like. Another way to say this is your familiar form, y equal cube root of x. That's what that is, actually. And there you go. Now y equal cube root of x actually is going to look something like this, right? So that's fine. And we are revolving this this portion of the curve right here. This portion is being revolved about the y-axis. So the formula is going to be 2 pi gy 1 plus g prime y. Well, our gy, that's what this is. That's a function of y, gy. And you just plug in for that. Take the derivative of y cubed is 3y squared, right? That is g prime y. And that's what goes in here. And then you can set up the integral this way. And of course, this would be integrable. You can use a u substitution because it's a good thing we have y cubed on the outside, dy. So if you want to pursue this further, you have to let u be 1 plus 9y to the 4th, and your du would be 36y cubed dy. Okay, and then of course, you got y cubed dy, and don't forget to change limits of integration, right? The limits of integration if you want to stay with variable u. So your limits of integration with u, when y is 0, u is 1, and when y is 1, u is 10. There you go. That would be limits of integration. So we can see if you would like to finish this exercise. All right, next I'm going to take a look at some of these exercises. Okay, so let's try to do some of these exercises. I'm going to look at the ones that I have circled here, these exercises. Let's begin with exercise number 4. In exercise number 4, the question reads, find the arc length of the graph from A to B. So I have number 4 actually down here. So let me work on this one. So we want to find the arc length, right? So let's see. In this case, we are given x as a function of y, right? X is equal to g of y. So what I need to do is, here's the actual formula for the arc length. Therefore, is going to be the integral from c to d, right? Because I'm given a function of y. So it's going to be integral from c to d of the square root of 1 plus dx dy squared dy, right? And let's see. Let's actually, I need to find the derivative, right, in order to complete the integrand. So let's actually begin by taking the derivative dx dy. Which is fairly straightforward. Derivative of y cubed over 6, that's going to be 3y squared over 6, plus derivative of 1/2 y. Remember, I'm looking at this equation. Derivative of 1/2, 1 over 2y. That's going to be 1/2 of 1 over y. And 1 over y is y to negative 1. So the derivative of that is going to be 1/2 negative 1 y to negative 2, which becomes 1 over negative 1 over 2y squared. Okay, so that's what I'm going to write. That's going to be negative 1 over 2y squared. And then let's combine the two fractions. The LCD is 6y. Actually, I can reduce these, right? There. So the LCD is 2y squared. Multiply the first fraction, top bottom, by y squared to build it to the LCD. So this becomes y fourth minus 1. So that's what dx dy is. Okay, now I can actually do my integral. The limits of integration on the y-axis go from 1 to 2. Note that so happens to be, 1 to 2 here, but of course not quite from 1 to 2. So you just be careful. The limits on the y-axis. So that's going to be from 1 to 2, and then the square root of the entire expression is going to be 1 plus dx dy squared. So that's going to be, I can actually do that over here. This is, let me do 1 over dx dy squared here. That's going to be 1 plus y to the 4th minus 1 squared over 2y squared. And this is going to give me the LCD again is going to be 4y to the 4th this time. So the 1, I can rewrite 1 as 4y to the 4th over 4y to the 4th. So that takes care of the 1. Plus, let's square the binomial y to the 4th minus 1. So when I square the binomial, I get y to the 8th negative 2y 4th plus 1. And then I can write this as y to the 8, combine like terms. 4y 4th minus 2y 4 is positive 2y to the 4th plus 1 divided by 4y 4th. Now the numerator actually can be written as y to the 4th plus 1 squared divided by 4y 4th. So that's the entire expression, 1 plus dx dy squared. And notice that's what the radicand is made of. So I'm just going to put this as the square root of that expression, which is going to be y to the 4th plus 1 squared divided by 4y 4th and then dy. Okay, and that's the integral from 1 to 2. Now I take the square root of this thing, and I'm just going to get y to the 4th plus 1 divided by 2y squared dy. And we don't need to take absolute value of this. Remember, when we go square root of x squared, the answer is going to be absolute value of x. But that's just to guarantee that we have a positive principal root. In this case, because y to the 4th is positive, y squared is positive, so that fraction is naturally positive. We don't need absolute value. Okay, and this is going to become integral from 1 to 2 of, I'm going to divide y to the 4th by 2y squared. So that's just going to be, actually bring 1/2 out. There, let me factor a half. This 2, I'm going to factor it. So y to the 4th by y squared, that's just y squared, plus 1 over y squared, that's y to negative 2 dy. So I can actually integrate this relatively easily. The integral is going to be 1/2, 1/3 y cubed plus y to negative 2 minus 2 plus 1 is negative 1 divided by negative 1 from 1 to 2. And this is going to give me 1/2. Let's see, plug in the upper limit. It's going to give me 1/3 2 cubed, right, minus 1 over 2. That's the negative. And then y to negative 1 is 1 over y. That's how I got the 1/2 minus the lower limit. It's going to be 1/3 of 1 cubed minus 1 over 1, which is 1. And this will give me 1/2. 2 cubed is 8. So this is going to be 8/3 minus a half. Negative 1/3 positive 1. Okay, and I can get the LCD here. to be 6. This becomes 16 minus 3 minus 2 plus 6. And all said and done, that will give me 17/12. And there you have it. That's going to be the length of the curve, of this curve. And the units, of course, would be in whatever units of measurements are: feet, inches, centimeters, kilometers, meters, whatever that might be. And there is exercise number 4 for you. Now let's take a look at number 10. Let's see. And in number 10, that's the one we're going to do. For exercise number 10, we want to find the arc length of the graph of the given equation from P to Q or on specified interval. Okay. So in exercise number 10, let me write that equation. Now, one thing that I will be doing is all the intermediate computations, I do it on the piece of paper if it's something that's or purely algebra, and then I just copy it down to my notes, because this way the videos don't get to be too long, the lectures. The point 3/8, 1, and point Q is 129/32, comma 2. I know these, like, why do we have this kind of numbers and expressions all of a sudden? They don't look like your usual polynomials and so on. It's because the integrand is the square root of 1 plus f prime x squared. Those integrands of that structure, got to be careful what kind of function you put in, because oftentimes those will not be integrable. That's why we have all of a sudden the equations that are kind of strange looking equations. Okay, so let's do x prime. Now remember, x prime here is dx dy, correct? That's what that is. The variable of differentiation is y. We're taking the derivative with respect to y. So derivative of 1/4 y/4 is going to be 4y cubed, and 1/4, 4 times 1/4 is 1, so that's just y cubed. Next, derivative of 1/8 y to second becomes 1/4 y cubed. Okay, and then I can get LCD, multiply the first expression top bottom by 4y cubed, so I can combine the two fractions. So here's my LCD, 4y cubed. This is going to give me 4y6 minus 1. And so that's just the derivative. Now 1 plus dx dy squared. If you know, that's the radicand of the integral that we will be integrating. So let me handle that separately. And this is going to be 1 plus 4y6 minus 1 over 4y cubed quantity squared, right? Quantity squared. And again, once I expand and get LCD, the LCD is going to be the denominator squared, which is 16y6. So there you go. That takes care of the 1, right? This one is 16y6 over 16y6 plus. Now I'm going to square the binomial. The binomial 4 squared is 16, y6 squared is y12. Negative 2 times first by second plus second one squared. And we do have like terms. The first and the fourth term in the numerator are like terms. So this is 16y12 plus 8y6 plus 1 divided by the denominator. And this time the numerator is 4y6 plus 1 squared. It's the square of a binomial. That's a perfect square trinomial in the numerator. That means I can rewrite it the way I just did. And that's good, because remember, we take the square root of that expression in our integration process. All right, so the length is going to be integral from 1 to 2 of square root of 1 plus, again, dx dy squared and dy here. So that's going to be the integral from 1 to 2 of square root of, remember, the whole radicand is this, of 4y6 plus 1 squared divided by 16y6 dy. And the integrand, we're simply going to lose the radical, take the square root of the numerator and the denominator. And again, we don't need absolute value because the numerator is positive. Now, the denominator, let me do the sidebar here. If I take square root of y to the 6, the answer is going to be absolute value of y cubed. However, and the reason we have absolute value because this is the principal root. Remember, that means the answer has to be positive. Well, look at the limit of integration. y is between 1 and 2. So y is positive. If y is positive, there is no need for absolute value, right? Okay, so for that reason, I don't need absolute value. Okay, and let's see, again, I'm going to divide the numerator, each term, by the denominator and bring out the 1/4. So that's going to be the integral from 1 to 2 of 4y cubed plus y to negative 3 dy. And the actual integration now, that's going to be y to the 4th over 4, the 4's cross out, minus 1 over 2 y squared. That's the integral of y to negative 3. Remember, negative 3 plus 1 gives you negative 2. That's why y is in the denominator. Divided by negative 2, and there you have it. Right? So it becomes, that's your divide by negative 2 part. Evaluate it from 1 to 2, and the upper limit again is 2 to the 4th, which is 16, minus 1 over 8 minus 1 to the 4th minus 1/2. So this is just 1/2, negative 1/2 with a negative on the outside. And the first parentheses is 16 minus an 8. 16 minus an 8 minus 1/2. So the whole thing, when I did, you should get 123 over 32. Okay, that's working the details of the arithmetic of those numbers. All right, so there is number 10. Next, we're going to take a look at number 14. Same segment. So we're going to try number 14, find the arc length. In exercise number 14, this time y is a function of x, right? And the function of x is x cubed over 3, or 1/3 x cubed, plus 1 over 4x, between 1 and 3. So this time dy dx, or y prime, is given by the derivative of x cubed is 3x squared. The 3's cross out, so that's just x squared. Next one becomes 1 over 4x squared. And then get LCD, combine those two fractions. The LCD is 4x squared, so multiply that by x squared. We get 4x4 minus 1. And then 1 plus dy dx squared, which is the radicand of our integrand, is going to be 1 plus square the fraction. Square the fraction, that's going to be 4x4 minus 1 squared divided by 16x4. And if I combine like terms, So actually, before I combine like terms, I combine the fraction. At this point, this is the 1, right? So that's, I handle the 1 that way. Now, square the binomial, we get 16x8 negative 8x4 plus 1. And 16x4 minus 8x4, that gives you 8x to the 4th plus 1 divided by 16x4. And again, the numerator ends up being a binomial, square of a binomial. You can write it like that. It is factorable. Okay. And if you want to see like how is that factored, I'm just working on the numerator. 16x to the 8, I'm going to go 4x4, 4x4. That product would be 4 times 4, 16. X to the 4th times x to the 4th. You combine the exponents, not multiply them. Gives you x to the 8. And then two numbers multiply to 1 to get the last term. So I'm going to go 1 and 1. The OI, the O and the I in FOIL will give us 4x4 and another 4x4 makes it 8x4. So you can actually factor it this way. That's how I got to the last step here. Good. Now we can actually write the arc length. The integral goes from 1 to 3 of square root of 1 plus, again, f prime x squared dx. And again, all of what I just finished earlier is 1 plus. That's why I did 1 plus that. You see that? So we don't have to do it inside the integral. That's going to be 1 to 3. And when I take the square root of that result, let me just put 4x4 plus 1 divided by 4x squared dx. Okay. Now, we can again divide, let me factor the 1/4 out and divide the binomial by the denominator. The first one, we're going to get 4x squared plus x to negative 2, and then there's dx. And that's equal to 1/4. Parentheses, the integral of 4x squared is 4x cubed over 3. And the integral of x to negative 2 is going to be x to negative 2 plus 1 is negative 1 over negative 1. So that's negative 1 over x. Evaluate it from 1 to 3. And then we're just going to plug in the upper lower limits fundamental theorem. So it's going to be 4 times 3 cubed is 27 divided by 3 minus 1/3 minus, plug in a 1, we get 4/3 minus 1. That's going to be 1/4. 4 times 9, that's 36. Negative 1 is positive 1. On the fraction side of things, we have negative 1/3, negative 4/3. Right? Which combined gives you negative 5/3. The LCD is 3. Right? In here, the LCD is 3. So that's going to give me, here's 3 multiply, 36 and 1 is 37. 37 times 3 is 81. So it's 81 minus 5, right? That's negative 1 minus 4 thirds. 81 minus 5 is 76. That's 76 thirds. And of course we can, let's see. Hold on, let me make sure I did this right. Oh, okay. Actually, let me see. This 81 is wrong. 3 times 37 is 111, not 81. That's 111. Okay, it looks right now. And 111 minus 5, that would be 106. And divide the 2's out, you get 53. So the final answer should be 53/6, and that should be in reduced form. Okay, so there is exercise number 14. Now let's take a look at, after number 14, we're looking at number 20. In exercise number 20, question reads, write an integral given the arc length of the graph of the equation from P to Q or over the indicated interval. Do not evaluate the integral. So in number 20, we simply want to set it up. So and the curve is x equals secant y, and we're using these points. We just want to set up the integral in number 20. Okay, so for exercise number 20, x was secant y. Therefore, dx dy, the derivative of secant, is going to be secant y tan y. Well, actually, this is x as a function of y, right? So it's, yeah, it is dx dy. Because it's y, we're integrating, we're differentiating with respect to y. Okay, so the arc length is therefore given by the limits of integration. Now it's on y. So for exercise number 20, the y goes from negative pi over 4 to 0, right? So I'm going to go from negative pi over 4 to 0 of square root of 1 plus secant squared y tan squared y and then dy. Okay, and that's what number 20 is. We just have to set it up. Now this one, that's what I was saying. We got to be careful with the function we choose, because these are very difficult to integrate, if not impossible. If we cannot integrate, by the way, an integral, we usually use numerical integration to approximate it. All right, and that was number 20. Now we're looking at this segment, number 34 and 38. Both of those. Find the area of the surface. So we're looking at surface of revolution now. Okay, find the area of the surface, and obtained by revolving the given curve about the indicated axis. So in number 34, we are revolving that equation about the y-axis. True, about the y-axis. So let's see how this is going to turn out. Okay, so this is number 34 is the one we're going to do right now. Now, because we are revolving about the y-axis, so I can actually do this without graphing this curve, because most of these curves, especially like the ones that you're looking at, this one, they're more complicated to graph unless we use a graphing utility. But I really don't need to do that just for this specific section. We don't need to graph it. I'm given the limits of integration when I'm given the y values. Remember, about y-axis, you use the limits that go with the y-axis. About x-axis, you go the limits that go with the x-axis. So let's do number 34. We want surface of revolution. In exercise number 34, the equation is x equals 1/6 y cubed plus 1 over 2y. And there you go, y lies between 1 and 2, and rotation is about the y-axis. So notice again I have a function of y. So in this case, g prime, if you will, the derivative is going to be y squared over 2 negative 1 over 2y squared. And then we can combine this as one fraction. The LCD is 2y squared. So that's what you will get. And 1 plus g prime y squared. Remember, that's the radicand for the square root that you will see ultimately like that in the integrand. 1 plus g prime y squared makes this as, here's the form of 1 that I need, plus y to the 4th minus 1. Actually, we want that squared. Hold on. 2y squared. We're squaring that. So actually, I want a different form of 1. Let me just write that as 1 plus still. Because once we square the denominator, we get 4y fourth, and that's how I want to rewrite the 1. Okay. So it's going to be 4y to the 4th, and then expand the binomial, y to the 8, negative 2y fourth plus 1, divided by 4y fourth. And this will give you, the denominator is 4y fourth, so you get y to the 8. We have a couple of like terms. 4y fourth negative 2y fourth, that makes it plus 2y to the 4th plus 1. And again, we can write the numerator as a square root of a binomial, y to the 4th plus 1 squared, divided by 4y to the 4th. That's all of the radicand. The formula for rotation, surface of rotation or revolution about the y-axis was 2 pi c to d, and then remember x ds, where x is the distance from the y-axis to the curve. That would be like the average radius. ds is the differential of arc length, right? ds would be square root of this expression. And now we're good to write this one. So this is going to be 2 pi. Limits go from 1 to 2 of x. And this is what x is. It's 1/6 y cubed plus 1 over 2y, right? That's what x is. And then square root of y to the 4th plus 1 squared, divided by 4y to the 4th, and then of course dy. Okay, and there we have it. Again, this part is what ds is, differential of arc length. So that's going to give me 2 pi 1 to 2 of let's go y cubed over 6 plus 1 over 2y. Square root just gives you y to the 4th plus 1 over 2y squared. And there's dy. Okay, and let's see, what am I gonna do next? We can the second factor in the integrand. I'm going to divide those. This one. Divide y to the 4th by 2y squared. That's going to make it y squared over 2 plus 1 over y squared. And then dy. Okay. Let me make sure I got this one correct. Okay, yeah, it looks good. Of course, you needed 2 here. Oh, one thing I can do is we can actually cancel the 2 here and the 2 here. So I no longer need those 2's, which is fine. Let me do them here now. There you go. Therefore, this is going to be pi integral from 1 to 2, and I can just FOIL these now. Y cubed over 6 times y squared, that would be 1/6 y fifth plus y cubed over 6 times 1 over y squared. That's going to make it y. It's going to make it 1/6 y. I'll multiply those together. Okay, plus 1/2 y plus 1/2 1 over y cubed dy, like that. Okay, now these two combine, 1/2 and 1/6. A 1/2 and 1/6 combines to 3 and 1/4, or 2/3, right? So this is going to be pi integral from 1 to 2 of 1/6 y to the 5th plus 2/3 y plus 1 over 2y cubed dy. And of course, each of those we can integrate piece by piece. The first integral, y to the 5th, is going to be y to the 6 over 6, so it's 1/36 y to the 6th. The second one is going to be y squared over 2, so that's 1/3 y squared. The 2 in the numerator of 2/3 cancels with the 2 from the resulting integral. And 1 over y cubed, that's going to be, remember, that's y to -3. The integral of that is going to be y to -2 over -2. So that's just going to make this -1 over 4 y squared then. The 2 times 2 makes it 4, the negative is there, and of course the y squared is, that's the y to -2 part. So you can verify that. Limits of integration run from 1 to 2, and let's see, you plug in the upper and the lower limits in this one. Let me do that. Okay, and if I did this right, I got 47 pi over 16. Again, you can do the arithmetic of the fundamental theorem in this one, but that's the answer to number 34. Okay. Now following number 34, I believe the next one was number 38. Yeah, this one. Number 38, 1/3 square root of y. Okay. Let me write this one down. Okay. Well, let's do this one. We're going to revolve this curve about the y-axis. So, first of all, we can actually let's make our x a little easier to work with. Because I'm about to take the derivative of this, right? And it's easier if we break it off. So that's going to be what? Square root of y, and that's going to be 3 minus y. And again, from 0 to 3, because y lies between 0 to 3, square root of 3 minus y squared is just 3 minus y. If we didn't have this information, you would have to put absolute value to guarantee that the answer will be positive. But between 0 and 3, this thing will be at least 0 between 0 and 3, right? You can try it. When y is 0, you get 3. When y is 3, you get 0. So your square root ranges from 3 to 0. So it's for that reason which we don't need absolute value. Okay. And now I can write this as, let's see, if I multiply now this times 3 and then times that, what do I get? The 3 times 1/3, that's just 1. Square root of y is y to a half minus 1/3. And the square root of y times y, that's y to a half times y. I know negative comes to the outside, and it's here. There. So that's going to be y to 3/2, right? Again, you can see how that happened. Okay, now I can actually take the derivative. So if I do derivative of x with respect to y, that's going to give me derivative of y to a half is going to be 1 over 2y to a half, right? Negative 1/3. The derivative of y to 3/2. 3/2 minus 1 is 1/2 over 2. Right? Okay, so that's hold on. Let me show you. So I'm doing 1/3. Derivative of y to 3/2 is going to be 3/2. Y to 3/2 minus 1 is 1/2. Those cross out, so this is actually going to be 1 over 2y to 1/2 negative 1/2 or y to 1/2 over 2. Now we can combine this. The LCD is 2y to 1/2. That's going to be 1 minus multiply. I need to multiply the second fraction top bottom by y to 1/2, and that's going to be 1 minus y over 2y to 1/2. Okay, now I need to do the, remember the expression under the radical sign. I'm going to do 1 plus dx dy squared, right? Square root of that dy, if you will. That's eventually I'm going to have to do that, right? So and that means I'm going to have a square root of 1 plus, well, dx dy is this, right? You square it, we're going to get 1 minus y quantity squared divided by 4y. That's 2 squared in the denominator, and y to 1/2 squared makes it y. And here's dy. Now if I combine in the radicand, I get 4y plus square the binomial. That becomes 1 minus 2y plus y squared. And there is dy. So this becomes y squared plus 2y plus 1 over 4y square root of that dy. Now the numerator is simply y plus 1 squared, right? Over 4y square root of that dy. So what I've done actually here is I've done the differential of arc length, right? That's your ds. That's the differential of arc length. So my differential of arc length, that's what this is. ds is going to be square root of the numerator is y plus 1, and square root of the denominator is 2 root y, and there's dy on the outside. And again, if I divide the numerator by the denominator here, I'm going to factor the half out. I will get y to 1/2 plus y to negative 1/2 dy. And we are good to go. There's your differential of arc length. So the surface of revolution is going to be 2 pi, and the integral goes from 0 to 3 of x ds. There you go. Because rotation is about the y-axis, so you look at the limits of integration on the y-axis. And now I can actually integrate this. It's going to be 2 pi 0 to 3 of x. Now remember, x was given to be y to 1/2 negative 1/3 y to 3/2. We were given that. There you go. That's what x was, right? So we just wrote it. And remember, instead of putting that, we actually simplified it to this. So that's the version, that's the form I used in the integral. And times the differential of arc length times this, which is going to be 1/2. Let me do times 1/2 by, let me do it this way. Parentheses y to 1/2 plus y to negative 1/2, and then the y. The 2 here and the 2 on the outside cross out, so that's just pi. Integral from 0 to 3 of. Now we can distribute here, right? y to a half times y to a half, that's just y. Y to a half times y to negative a half, that's just 1. That's y to 0, which makes it 1. And then distribute here. Negative 1/3. Y to 3 halves plus y to a half. You add the exponents, we get y squared. And negative 1/3. Y to 3 halves times y to negative a half. So we add those exponents, and those add to 1. Okay, so we have y minus 1/3 y, that's 2/3 y. Let me write what I have. Negative 1/3 y squared plus 2/3 y plus 1 dy. That's what we have. And again, I can integrate this now easily. The integral of negative 1/3 y squared is y cubed over 3, so it's negative 1/9 y cubed. 2/3 integral of y is y squared over 2, so this is actually going to become 1/3 y squared, and integral of 1 dy is just y from 0 to 3. The lower limit into that polynomial gives you 0, so I'm just going to plug in the upper limit, namely the 3. Negative 1/9 3 cubed, that's 27, that's good. Plus 1/3, 3 squared 9, not so good. Plus 3. So the first fraction becomes 27/9, that's negative 3. Actually, this isn't bad either. 9/3, that's 3 plus 3. So it looks like the answer is going to be 3 pi. And there we have exercise number 38. The key is to work these to where the integrand is something. And in this course, again, it always works that way. It's going to be something in this form where you take the square root of it. And ultimately, following a few steps, it becomes integrable. Okay, let's see, what's the next one? I'm going to look at, in our list of exercises, we did good, we had 38. Let's do this last one for this lecture. Exercise number 44. Question reads, verify that the surface area of a sphere of radius r is 4 pi r squared. Now remember, we know that from geometry, right? So that's interesting. How do they come up with that formula? And we're going to prove or show that formula, where that formula come from. By evaluating a definite integral, now because we are looking at general formula for any radius, that's why in the equation of a circle, we're looking at the general radius r. Here y is 0, and we're going to revolve this about the x-axis. Okay, so we're doing number 44. Now we're told y is positive, right? Because here, when I solve for y, I'm going to get the square root of r squared minus x squared plus minus. We're told r is positive, so I'm just going to stay with a positive root here. Let's take a look at number 44. Let's derive the formula for the surface of a sphere. So our equation y, we said, is square root of r squared minus x squared. Now y prime, right, which is dy dx in this case, is going to be what? R squared minus x squared to a half. We want to find the derivative of that, right? Let me write it here actually. R squared minus x squared to a half, its derivative. So we're going to bring the half in front. That's r squared minus x squared. And then the half minus 1 is negative 1/2. And then remember, chain rule. This is a function composition. The derivative of the inside is negative 2x. The 2 in the denominator and the 2 in the last factor cross out. So this is going to be, but notice it's negative. right? The negative stays. So that's going to be a negative of x over square root of r squared minus x squared. So that's just a derivative. Now, we're going to do the differential of arc length, right? So to do that, I have to do 1 plus y prime squared. So that would be 1 plus negative of x over the square root of r squared minus x squared squared. And that's just going to make it 1 plus x squared divided by r squared minus x squared. We lose the radical in the denominator because we're squaring the fraction. And then the LCD here, again, I'm going to write, this is the form of 1 that I'm going to write it as r squared minus x squared divided by r squared minus x squared. See, that's the 1. That takes care of the 1. And then plus the numerator, which is x squared. And those are opposites, and all we have here is namely r squared divided by r squared minus x squared. Okay, and now we can do our integral. The surface is 2 pi. The limits of integration go from negative r to r, correct? And it's y ds. Okay, so this is a function of x. So imagine we have a half circle. This is negative r to r. There you go. This is exactly what it is. Square root of r squared minus x squared. And there. We are revolving this about the x-axis. And that is what dx is. And y, of course, is this distance from right in here. This is what y is, right? Actually, something I need to correct here. I don't need to do a vertical rectangle. Remember, we're revolving the curve. The curve is being revolved, right? Not the region, not the area underneath it. That curve is being revolved. It's like a string or piece of wire that's revolving. So actually, this is what we need. That's going to be the average radius for, remember, the frustum of the cones that are going to be generated. And there, that's what y is. So y is the average radius. Okay, and this is going to be 2 pi negative r to r. Y is square root of r squared minus x squared. And ds is going to be the square root, right? It's going to be square root of r squared over r squared minus x squared, and then dx, right? And that's what that is. Okay, one more step. We need to simplify the radicand. These two actually simplify nicely. And the reason is because, there you go, those cross out. And square root of r squared is just going to be r, correct? So that's going to be r. And since r is taken to be positive, again, when we take square root of r squared, usually we have absolute value of r, but because r is positive, there is no need for absolute value. Okay, so that's going to be r and then dx. Now r is a constant, right, with respect to the variable of integration, which is x. So I'm going to bring the 2 pi r out and simply integrate from negative r to r of dx. And the integral of dx is just going to be x, correct? For this one, that's going to be 2 pi. And remember, we brought the r out, 2 pi r. And the integral of dx is just x from negative r to r. Okay, here is 2 pi r. Now we're going to plug in the upper limit is r minus plug in the lower limit, negative r. And that's going to be 2 pi r. R minus minus r, that's 2r. 2 by 2 gives you 4 pi. r gives you r squared. And there we have the 4 pi r squared as a result of that. Okay, and that is indeed what the formula for the surface area of a sphere is. So hopefully you were able to follow everything we've done, and we are done with this section, arc lengths and area of surface of revolution.